Dear colleagues, just few, please. Как всегда вовремя. Надо выключить, да, микрофон.
И звук, да?
Или
чтобы звук был только отсюда?
Нет, лучше, чтобы отсюда. Потому что микрофон будет отсюда.
А звук?
И звук тоже. Он должен из одного места быть. Я думаю, что хватит будет.
Да.
Ну тут основной звук будет. Enter. Нет, не работает. Okay, we are ready to start. And I'd like to present myself as a speaker. So I will talk about some recent advantages in the theory of full Toda system, which is due to recent joint work with Sharygin and Chernyakov. But I will speak about some related topics, about some geometrical aspects of the full Toda system. So the principal point is the QR decomposition and the method of solving the Toda system by this method, and the geometry of like varieties. Okay, one of the results, but not the recent one, is obtained in collaboration with Alexander Sorin. The Toda open chain is defined like a Hamiltonian dynamical system. So it's a system defined by the Hamiltonian function, which has a potential kinetic and potential term. The potential term describes the pair interaction of particles with some exponential potential, and was chosen for the reason of integrability. So the dynamical system described by this Hamiltonian with the common Poisson brackets can be so is integrable, for example, in the sense of the existence of the Lax representation for the system. The Lax operator here is three diagonal symmetric matrix. Those elements are related with the initial variables by these formulas. These variables are called the Flaschke variables in the context of the Toda open chain. And the Hamiltonian H is a spectral invariant for the Lax operator. Precisely, it is a trace of the second power of L. And this system is related to the quark algorithm, which is very known in application, in calculating applications. So it works in the following way. Let A be a real matrix. We can define a discrete dynamics on the space of matrices in such a way that the next element, the next matrix a k plus 1, is defined by the QR decomposition of AK. So AK is equal to QKRK, and if we change the order of these matrices, we obtain new matrix AK plus 1. This discrete dynamics, in fact, allows to find the spectrum of the matrix A. So it's a good algorithm for calculating the eigenvalues and eigenvectors of the matrix A. Precisely for a symmetric matrix A, this series tends to a diagonal matrix in the limit k to infinity. And this diagonal matrix is similar to the initial matrix, and hence it produces the spectrum of the matrix A. Okay. Dramatically, the dynamics, the continuous dynamics of the Toda system, the open Toda chain, is related to the QR decomposition by the following observation. Let L0 be a symmetric three-diagonal matrix, and let us consider the QR decomposition of the exponential of this symmetric initial matrix by this form, Q of t multiplied by R of t, and then consider the matrix L of t, which is the conjugation of L0 by Qt, which is the part of this QR decomposition for the exponential of initial matrix Lt. The statement is the following, that it is the solution for the Toda open chain with initial value L0 equal L0. And this solution is related to the QR decomposition, to the QR algorithm, sorry, by the following theorem. Let Lt be a solution for the Toda system, then the exponentials of the values of the Lux operator in discrete times are the matrices obtained by the QR algorithm. So, in this sense, the Toda chain is a good way to diagonalize the matrix. If we can switch on the Toda flow on the space of matrices which are of our interest to diagonalize them. The full Toda system is natural generalization of the open Toda chain, and it can be obtained by changing the space of three diagonal symmetric matrices to general symmetric matrices. I'd like to introduce the notation for the matrix A, which is symmetric in the following way. So it is the sum of matrix units multiplied by matrix element Aij, which I'd like to identify with generators of the Borel lower triangular subalgebra B minus. I'd like to define some auxiliary matrices A, K, lambda, which are obtained by deletion of K right columns and K upper rows of the matrix A minus lambda identical operator. By the result of Deift, Tam A, the complete set of roots of all polynomials which are determinants of these partial matrices A, K, lambda constitute a commutative family with respect to the natural Kirillov constant bracket on in fact on the field of fraction of this symmetric algebra, which is the Poisson algebra for our system. Another basis of integrals for the full Toda system can be given by the coefficients of polynomials p, k of lambda, which are just the determinants of these partial matrices A, K, divided by the highest coefficients of these polynomials. So these affine coordinates produce the complete commutative family in this system, for this system. And this commutative family can be arranged into a very natural generating function, which is obtained as follows. Let us consider an anti-diagonal matrix omega epsilon with different degrees of this formal parameter epsilon on the anti-diagonal, and then we consider a characteristic polynomial of this type. So A is this symmetric matrix, which is normalized by the spectral parameters z minus 1. There is a constant term, magnetic term, in the framework of the Godin system, and we consider this characteristic polynomial and extend it on homogeneous components on variables z minus 1 and lambda. Each such component, I, k, z, lambda, epsilon, is a polynomial on epsilon. And we choose this the leading term of this polynomial with respect to epsilon, and in fact it reproduces the chopping integrals for the full Toda system. So these are the formulas for relating the coefficients of this generating series and all chopping integrals for the Toda system. So the QR decomposition at the beginning of my talk is not accidental here. The open Toda chain and the general full Toda system are the examples of the very general Adler-Kostant-Symes scheme, which is one of the efficient methods to construct integrable systems from some trivial ones from one point of view. So this scheme works as follows. Let us consider a Lie algebra, which is a sum of two its subalgebras, not necessarily ideals, only subalgebras. We interpret the symmetric algebra of G as an algebra of function on the dual space of G, dual space G star. There is a natural projection map I from the symmetric algebra of algebra G to the symmetric algebra of its subalgebra. Okay, so it corresponds to the decomposition of the symmetric algebra of polynomials on polynomials with symbols in this in the Lie algebra. So the statement is the following: let f and h be G plus invariants in the symmetric algebra as G, and they commute with respect to the Kirillov constant bracket on S of G. Then the images I, F, and I, H commute with respect to the bracket in S G plus. It is important to say here that I is not a Poisson map. So it's some linear map, but it do not preserve the Poisson structure. That's why it is not a trivial observation. If, for example, we consider the decomposition of SLN Lie algebra as the sum of Borel lower triangular matrices and the Lie algebra of orthogonal group, then the space of functions on symmetric matrices, which is the space of functions, the Poisson algebra in the case of the full Toda system is interpreted as a symmetric algebra of S of the Borel subalgebra D minus. And the map I is just a projection along the orthogonal, special orthogonal Lie subalgebra. So it may be important to remark here that we apply this Adler-Kostant-Symes scheme to the commutative family of Godin Hamiltonians, choosing among them the subalgebra subspace of G minus invariant functions. And the construction, the chopping integrals that I mentioned, produces exactly this the subspace of G minus invariant elements in the general Godin commutative frame. Okay, this scheme is good for quantization. So let me remind the way to quantize this system. Let's firstly consider the definition of the non-commutative determinant. I prefer here to use just the simplest one. So it's the completely symmetrized determinant of the matrix with non-commutative elements. So B is a matrix with non-commutative elements, and its non-commutative determinant is just the expression given by the formula. There we sum over two elements of the symmetric groups, tau and sigma. Then we consider the generating series PQ, the quantum version of the characteristic polynomial in this case. And so here A is just the Lux operator. Those values now we interpret as element of some non-commutative algebra of the universal enveloping algebra of the algebra SLN. Omega epsilon is the same anti-diagonal stratifying matrix depending on some formal parameter epsilon, and we replace the spectral parameter lambda by the differential operator d over z. This generating series produce a commutative family for the quantum Godin system, and it is easy to choose among these quantum Hamiltonians, such Hamiltonians which are invariant with respect to the action of the Borel lower triangular subgroup. So to do this, we choose the homogeneous components of this expression with respect to z and d over z, and epsilon, and in all components we choose the lowest term with respect to epsilon, and due to some simple deformation principle, these coefficients commute in the universal enveloping algebra U of JLN, and they generate the coefficients of such polynomials represent the commutative family in this quantum algebra. And moreover, okay. In the quantum case, we can apply the quantum version of the Adler-Kostant-Symes scheme. To do this, we choose some normal ordering in U of SLN, and this normal ordering allows to construct a projection from the universal enveloping algebra of SLN to the quantum algebra related to the barrel subalgebra, the universal enveloping algebra of B. And so there is some subtlety related to the localization, but we should consider some ratios of quantum operators. But it is easy to show that the set of denominators substitute a multiplicative set, which is an array set, and we can consider the localization with respect to this subset. And the statement, the theorem of quantization state the following: that the ratios of coefficients of the coefficients of quantum characteristic polynomials generate a commutative family in the localization, in the appropriate localization, and they commute. And they are this is a quantization of the classical full Toda subalgebra. Okay, so it's just to recall some old result demonstrating that this generating series is a good way to structuralize the commutative family of quantum of full Toda Hamiltonians. There is another, there is another application of the full Toda system, and I like to recall what is the normal or non-split real form of Lie algebra. So let us define the Cartan decomposition with the help of Cartan involution. Cartan involution test. So let theta be a Lie algebra automorphism such that theta square is equal to 1, and the quadratic form b x theta y, there b is a Killing form, is positive definite. Then K, which is the eigen subspace of this involution with the eigenvalue -1, and P is the completion. So it's a subspace, eigen subspace with the eigenvalue 1. The Cartan decomposition is unique, and there is some relations. So K is a subalgebra, and P is some module of this algebra. And let A be a maximal commutative Lie subalgebra in P. Then the real form is called normal or non-split if A coincides with the maximal commutative subalgebra in the whole algebra G. So it's just to give you a definition, but for me the principal point is that for a quite large family of Lie algebras, we can state some important theorem. So let us suppose that G is a real algebra with those complexification is GC, and which is normal or non-split real form. The Weyl group of G is defined as the quotient of the normalization of the Cartan subalgebra by its centralizer. Okay. The Breuer order in the Weyl group is defined with respect to some set of generators, and it is a unique partial order determined by the following rule. Say that the generator W precedes W prime if a minimal word S of W prime in letters from this generating set representing W prime has the form, such form, there S of W is a minimal word for W. And the lengths of such of these words are called lengths of the element, denoted by L of W and L of W prime respectively. One can define real Brouwer cells X W and dual real Brouwer cells Y W in the flag variety by the B plus and B minus orbits of elements elements W. There is a theorem that the intersection of such real Brouwer cells X W and the dual real Brouwer cell Y W prime is non-empty if and only if the W prime is less W in Brouwer order, and the dimension of this intersection is exactly the difference of the lengths of such words. So the statement was known before our joint work with my colleagues in a complex situation, and was not realized in the real one. And we demonstrate it using the action of the Toda flows on the flag variety. Okay, so I give some details on the construction for the Toda flows on general non-split Lie algebras. So in this case, the Lux operator is represented by this form, and the M operator, which defines Lux representation, is defined and the M operator is defined as an operator of the projection to the compact Lie subalgebra, which is defined by the Cartan decomposition. So one can define the flows not on the symmetric matrices, or in this case, on the linear space P in the Cartan decomposition, but on the corresponding compact group. And these flows are defined by the formulas here. So here psi is an element of the group. This is in fact, it is the corresponding Lux operator, but we apply the projection of this Lux operator to the compact Lie subalgebra, and they apply the element of this Lie subalgebra to the element of the group. So it's a tangent vector to the corresponding group. And in fact, this system defined on a group, it preserves Brouwer cells and dual Brouwer cells, and hence preserve the intersections, and it is related to the initial Toda system by this formula. So if we consider the Lux operator defined by this formula, it reproduces the Toda flows on in terms of Lux operator. And the statement of invariance of Brouwer cells with respect to the Toda flows allows to control the dimension of this intersection. And the triviality of our result was that was due to so in fact it is sufficient to find one real point, one non-singular real point of the complex variety to demonstrate that this real variety has the proper dimension. But the points which are manageable for the Toda, for the intersection of Bria cells are singular. So it was not automatic the calculation of these dimensions, and it was done by considering the geometry of Toda flows on this space. Okay. Now this is a new part of the this subject. So it's a part of it's a generalization of the QR method to the full Toda system, and principally it is a way to how to solve all additional Dave flows in the Toda full Toda family. To do this, we introduce some special some highest Q powers of Lux operator. The first auxiliary element is this matrix, is this function. It is some minor of the matrix L, and then we consider some polynomial matrix value function tau k on SLN with values in GLN. Which are given by this formula. So this is a definition of tau k of L. It's an operator, and here we define the action of this operator on the vector V. It is given by this determinantal formula. It could be understood as some reduction of the kth skew power of the operator L, restricting to highest vectors in this representation. But exactly this operation is given by this formula. So, for example, tau 1 of L is just L, and tau the second operation tau 2 of L is given by the formula here. We consider vector fields Tk on the space of symmetric matrices, of full symmetric matrices, which are defined by this formula. Here, M is just the projection to the antisymmetric part, as in isospectral flows of the Toda system. But in place of the operator L, we consider this polynomial operation tau k of L. The solution of this flow, of this equation, can be obtained by the QR method. We should consider the exponential of not of L0 but of Tk applied to L0 multiplied by the time variable T. We consider the QR decomposition of this element, and just the traditional form of solution, but with the special Q, which is given by some generalized map Tk, gives a solution for these flows. And these flows are flows from the family of higher Dave Hamiltonians. So this vector field is Hamiltonian with respect to the Poisson structure on the space of symmetric functions, which is just the Kirillov constant bracket on B minus. And the Hamiltonian function hk minus 1 and minus k, so it's one of the coefficients in the hierarchy of Dave integrals, Dave Hamiltonian. And there is some generalization. So in fact, all flows of the full Toda system can be solved by the QR decomposition method. And this solution is given by the following operation. So let us consider some generalized gradient vector of the determinant of the Lax operator. So we consider generating functions, a function of gradients of all Hamiltonians from the Dave family. These are given by this expression. Their decay is a differentiation operator with respect to the upper anti-diagonal element of the matrix A. So decay is the composition of differentiation with respect to x, y, n, x1 n, x2 n minus 1, x3 n minus 2, etc., up to xk n minus k plus 1. So we consider such generating series and consider the linear operator J bold with such indices which is the gradient of this ratio. And the statement is the following, that the QR decomposition method with respect to such linear operations, I'm sorry, not non-linear, but polynomial operation on the Lax operator produces solution for all higher Dave flows. Okay, so we were interested by this construction particularly for geometrical reasons, because this way to solve all Dave Hamiltonians shows that there is a stratification of these flows, and we hope that so it's a question 2. We hope that this could be useful in understanding some new geometric features of the flag varieties related to an additional stratification with respect to the full Toda flows. Speaking about QR method, it is particularly interesting for me to generalize it to the quantum case. And as far as I know, it is not understood even in the simplest open Toda chain case. And the first question is also very interesting. So it is known that the full Toda system is super integrable system. So there are many different families of integrals commuting with this isospectral one, and algebraically they are related to alternative towers of parabolic subgroups, and we hope that it is related to that our method is could be applied for these different towers of parabolic subgroups, and it has some interesting representation theoretical meaning. Thank you very much.
You said about super integrable systems, it's quite general and quantum systems. They have more invariants than the dimension of the map.
Than the half of the
half, yes. N minus 1.
No. It's big. So the dimension of the space is n square over 2. The standard Deift family is something like n square over 4, but there are different families precisely of the same dimension. And all of them they are integrals of the central part of the just of traces of powers of the Laplace operator, which are called is a spectral.
And can you construct action angle variables just to confirm complete integrability in the proper sense?
Just not now. So some algebraic geometrical part of the story. We have not yet worked on this subject.
Right. So you only know that there are big families of commuting integrals.
No, we can solve them by QR decomposition.
Yeah, I understand. It's yes, it's exactly solvable. Yes. So far, there is no proof of complete integrability in the proper sense. I mean, you know that it's exactly solvable, but you don't know how to construct action angle variables.
Well, just may I make a small remark in this sense? Liouville theorem about complete integrability works in symplectic manifolds, on symplectic manifolds, and we work with Poisson manifolds. So
right. Yes, your Poisson structure is quite degenerate.
It's quite actually degenerate in many points.
Yeah.
So actually, completely you can hope about. You can ask about complete integrability on symplectic leaves, and in that case, yes, we just can. In that case, we can just use Liouville theorem, because the number of integrals is sufficient for that. But yeah, we don't know the exact way to express angle and action variables. That's to be shown.
So
yeah, right.
these extra integrals that you have in your super integrability, these extra integrals are Casimirs. So you may have your integrability from this symplectic case. Yeah.
Sorry, didn't hear you.
Yeah. So since you have more integrals than half the dimension, so your symplectic leaves will be the Casimirs. Yeah.
Yeah, there should be Casimirs. Yeah, there are lots of Casimirs actually. Just the first.
So you have the half of dimension of the map plus Casimirs, and you can restrict on these Casimirs, and you can.
You can actually count very accurately the number of independent integrals and the number of Casimirs, and it has been done by Yura Chernyakov. Yeah. So yeah, just the number, as far as the numbers are concerned, that's more or less proven result. But of course, we don't know the formulas for angles and actions. Yeah, that must confess.
Dima, could you please clarify the challenge you listed, the third one, in the last slide? I mean, what do you mean the quantum QR decomposition? What particular problem you want to solve? Can you clarify it, please?
I'd like to solve the quantum system, the quantum full Toda system.
But what do you mean solve the quantum? What do you want to see as a solution?
As usual, to find eigenvectors for quantum Hamiltonians.
So you say that even in the case of open Toda system, it has not been done?
I don't know. I don't know the result. I'm not familiar with it.
Okay, thank you.
Okay, I'm today an organizer and a speaker, so I decided to finish the talk. Thank you very much. Good evening.
Thank you.
Bye.
Thank you.
Bye.